what I would like to do now is I would like to look at an example. Let's calculate this de Broglie wavelength for two cases, a dust particle and an electron, accelerated, how you would accelerate an electron in a laboratory. You would probably put it in a parallel plate capacitor and crank up the voltage, right? So let's look at these common lab-like situations. Calculate the Broglie wavelength of a couple of accessible accessible examples, right? I mean, nothing too highbrow. Okay, so let's estimate the Broglie wavelengths for some cases. Example 1, a dust particle do you guys have any sense of how big a dust particle is? So, okay, the reason I always scratch my nose is because for some reason this spot has a lot of dust from the cooling vent and heating vent. But my point is they come in different sizes, but it's typical to have a dust particle like a micrometer, like micrometer size. And let's say it's a round dust particle. Let's see. One micrometer. We go, it's almost like approximately, but it's even more approximate, just an order of magnitude. Okay, just 1 micrometer. Mass, how heavy is a dust particle? Huh? 10 to the minus 15 kilograms. That's a reasonable mass. Okay, and moving with speed, how fast dust particles move. Again, you should be able to kind of get an order of magnitude estimation, right? Is it kilometers per second? No. Is it meters per second? No. Unless it's in some kind of a stream. Is it millimeters per hour? No, that's too slow. You will see in dust particles. Millimeter per second is a reasonable. 1 millimeter per second. Okay. Okay, so lambda equals h over p. There's a clearly non-relativistic dust particle, so that's h over mv. Let's plug in chug. Well, h is really small. You see, 6.6. That's the brouhaha. H is really small. I'm not gonna put units, and this is 10 to the minus 15. You have to work in kilograms, meters, seconds, times 10 to the minus 3 meters per second. Right? I think I should put joule seconds. This is what? Kilograms, and this is the minus 3 meters per second. Okay. Now this joule seconds is the same as meters squared kilograms over seconds. So kilograms cancel, meters cancel, 1 over seconds cancel. And so we get 6.6 times 10 to the minus 16 meters. Okay, so maybe 10 to the minus 15 kg is a little bit too small if mass equals 10 to the minus 13 kg, which is, I think, maybe more realistic. Then you get a wavelength is something like that. So if this is 10 to the minus 15 meters, right? And then now it would be 10 to the minus 13 meters. In any case, these are very small numbers. They're much smaller, much smaller than even a size of a typical atom, right? A characteristic size of a, again, atoms come in different sizes, but it's something like an angstrom, 1/10 of a nanometer. Both of these numbers, the 10 to the minus 13 is 10,000 smaller than a nanometer. Okay, so you have to kind of, when you get lengths, and when we deal with particles, we deal with very small lengths, and they start to lose meaning. 10 to the minus 13, to the minus 15, to the minus 20, like, what are all these numbers? You have to kind of have a sense of how they compare with other standard small things, such as interatomic spacing in a crystal. Well, a characteristic size, characteristic atomic dimensions, or like typical dimensions that characterize sizes of atoms, they are of order angstroms, meaning 10 to the minus 10 meters, okay? And this is at least 1,000 times smaller or 10,000 times smaller than an angstrom, okay? It's a very small wavelength. Okay, so we'll come back to this. Now let's do another example, okay? But by the way, what makes this small, where does the smallness come from? It's right here. This is where the smallness comes from, right here, okay? The Planck's constant is what makes all these things really small. Okay, so example two. What else? How about an electron accelerated across a potential difference, right? You put an electron in a parallel plate capacitor, you crank up the voltage, the electron comes flying. That's how old-fashioned TVs used to work, right? It's nothing super duper, right? So an electron accelerated across a potential difference. Okay, so example, inside a parallel plate capacitor. Take capacitor, put a poor electron, and let me blow it up. Okay, you hook up a battery, hook up your battery. Okay, and then you put a tiny poor electron, and let's see. So I guess maybe you would put an electron. Let's see. So this is a positive. This is a negative. The electron will want to go here. Let's put our electron where it belongs. Okay, and it will go towards the positive plate. Okay. Okay, let's do the calculation. Well, what's the electric field? E equals, no, not the electric field. I'm sorry. What's the kinetic energy? Right. So the electron exchanges potential energy for kinetic energy. Right. So potential energy gets exchanged for kinetic energy. Okay. So Ke initial equals 0. Ke final equals the change in the potential energy, right? What's the change in the potential energy? It's Q times delta V. When an electron goes across a potential difference delta V, its potential energy changes by Q delta V, and so its kinetic energy also changes by Q delta V, or minus Q delta V, right? And so if it started with 0 kinetic energy and it goes towards the positive plate, it will acquire this much kinetic energy. Okay, so we have Q delta V equals 1/2 mv final squared. Okay. Now, 1/2 mv squared is another way to write that is 1/2 p squared over m. It's a very useful way of writing kinetic energy in terms of momentum. In quantum mechanics, we deal mostly with momentum, not velocities. Okay, so then, so I have Q delta V equals 1/2 P squared over M, dropping the subscript final. Just, it's the P at the end, right? So P at the end of the journey, the momentum increases. Okay, so let's see, wavelength. So, okay, so let's do this. So now let's solve for P. P equals 2Q delta V times M taken square root, right? Now the Broglie wavelength equals H over P, which is H over square root 2QM with the square root of delta V. And when you put in the numbers, you can do that for yourself. You would get 1.2 times 10 to the minus 9 divided by the square root of the potential difference. And the whole thing is in meters, okay? Now, what kind of potential differences can you apply? Oh, you put a 9-volt battery in the lab, you can plug it into the wall, you can get 100 volts, right? So for delta V of several hundred volts, we get something like, let's say if delta V is 100, square root of that is 10, and then the minus 9 divided by 10, it's like 10 to the minus 10. Okay, so we get something like 0.1 nanometer, okay? And that's actually very comparable to sizes of atoms, to interatomic spacing. Okay, so this is comparable to atomic dimensions, okay? And then, you know, crystal in atomic spacing, etc. I find that students have a difficulty with the idea of something being comparable, okay? Because all these years you've been taught to put numbers into a formula, get a number out. And so you're used to dealing with exact numbers. So if I'm trying to take a couch through a door, and the door has the width 1.3 meters, what matters is not that the couch is exactly the size of the door, but what matters is whether the couch is much larger than the door or much smaller than the door, or even smaller than the door, okay? So we're interested in orders of magnitude. Yes, it's true that we might get to a point that we really have to get it down to the millimeter. And in some cases you do. But in most cases, we want to know what can you carry through the door? You can carry a shopping bag because it's much less than the door. You can go through the door yourself because you're much narrower than the door. You cannot carry a boat through the door because it's much larger through the door, right? So in what we're doing here, we're trying to do estimates, an order of magnitude estimate. Is something millions, is something trillions, or is something 10 to the minus 5, right? So that's what we want to do. Does something take seconds, hours, days, or years? So these are all order of magnitude estimates. And that's really what we need for our purpose right now. And that's actually how most of calculations are done. So if you get a job as an engineer, you will see that you don't always need to calculate something down to the last digit, right? Okay, so that's what we mean by comparable. And I will use that language again and again. Anyway, what is the lesson? So here you get 0.1 nanometer. And in this case, you get 10 to the minus 4 nanometers, right? So this is equal to 10 to the minus 4 nanometers. This is much less than atom sizes. This is comparable to atom sizes. So what does it mean that a wavelength of a dust particle is significantly smaller than the wavelength of an electron? What does the discrepancy in these two numbers tell us? What can we learn from it? Recall how the idea of an electron as a wave came about in the first place. It was that when electrons were sent through double slit apparatus, right? It's our conceptual workhorse, double slit apparatus. Although it's not just a thought experiment, it is a real thing, but we use it for thinking, right? So the idea of an electron as a wave came about when we thought of electrons being sent through the double slit apparatus. And when they were sent through the double slit apparatus, they displayed an interference fringe pattern that told us, aha, waves, interference fringes, waves. Rest assured that if we shoot dust particles through slits all we want, we will not get interference fringes, okay? I'm sure you believe me. So why? Interference fringes, waves. No interference fringes, particles, right? So dust particle behaves as a particle in a normal sense of the word, and electrons have the ability to behave as waves, at least when we subject them to the double slit apparatus. What is causing interference fringes? Like let's get back and let's put on the Phys 2 hat on. Recall what causes interference fringes with, so example, with two slits. Okay, so here's your double slit. Here come waves. Okay. And now the waves will form circular pattern. This circular spreading, it's called diffraction. Diffraction of waves just means spreading of waves. If a wave, imagine there's a wave breaker and there's a hole in the wave breaker. Imagine, just visualize that water, ocean wave coming through the jetty or through the wave breaker, coming through the hole in the wave breaker. It forms kind of a circular pattern, right? So you would say the wave diffracts. It's just a fancy language for spreading out of a wave. I'm gonna take waves with much smaller wavelength. Okay. This is much smaller. Forget de Broglie, forget quantum mechanics, just waves through two slits. What would happen? Pause the video, think about what would happen. The spreading out of waves decreases, okay? So the waves hardly spread out. They sort of spread out, but much slower, okay? And here, huge spread out, huge spread out, small spread out. Small spread out. They do spread out, but smaller the wavelength, the smaller the spread out. So evidently, and you know that from when you talked about the single slit, right? So when we talk about, recall, one slit diffraction, something really funny is happening with my iPad, you have a pattern like this, right? And what was this? Well, you have a sine theta equals lambda. So say sine of a small angle, sine of theta is approximately theta. And so you get theta goes like lambda over a. You see, so right here, this is it right here, lambda over a. So if you keep the slit width constant, if you keep the width of the slit the same, you make lambda smaller and smaller, the angle of the spread becomes larger and larger. And if you keep the slit width the same and you make lambda smaller and smaller, the angle of the spread becomes smaller and smaller. So here's this angle of the spread. It goes like lambda over a. So you can increase the spread either by decreasing the slit width for a fixed lambda or increasing lambda for a fixed a. So that's that crisscross effect. The smaller is the slit, the larger is the spread. Okay? So that's a single slit effect I'm talking about. I'm talking about the spread here. You also have something similar for a two-slit formula. D sine theta equals n lambda. So the angle between the first fringe, second fringe, third fringe, and so on, in a two-slit pattern goes something like lambda divided by the slit separation. Okay, so there are two angles involved. One is the angle of the spread from each opening, and the other is the angle between first fringe, second fringe, third fringe. Both of those go like lambda over geometric size. Lambda over geometric size. Lambda over geometric size. That's what matters, right? So you see, theta goes like wavelength over geometric size. Okay? And so, right, so we have, this is a single slit. In double slit, you have a similar formula. Both go like lambda over geometric size. So as lambda goes smaller and smaller and smaller and smaller and smaller, all of these angles become smaller and smaller and smaller. As the wavelength gets smaller and smaller and smaller and smaller and smaller, the degree of spread becomes smaller and smaller and smaller. The degree of overlap here, you see here, you have overlap. I don't know what's going on here. So you have overlap, interference, little overlap, little or no interference. Do you see what I'm trying to get across? I'm trying to get across a concept to you. That as the wavelength becomes smaller and smaller and smaller in comparison to geometry, in comparison to size of experimental apparatus, in comparison to openings, in comparison to apertures, in comparison to separation between openings, and so on, all of these wave effects become less and less noticeable. It's still a wave, but for example, here there's little overlap. Little overlap means no interference, no fringes. If you want fringes, you have to go much further, because if the overlap is small, you have to go further to see to actually see the overlap playing any role. So in the limit of wavelength going to zero, spreading out also goes to zero. And now if you put a screen here, if you put a screen here, you will not get fringes. You will just get two bright spots, like you shoot two laser beams, right? So you shoot very small waves, or waves of, so this is tiny lambda, tiny in comparison to aperture sizes, slit separations, all that. And you place a screen, well, you see, you get very, very hardly any spread out. Right, so you get hardly any spread out. And so what you get is you just get two bright spots here. Yes, if you put the screen 5 kilometers down the line, eventually there will be an overlap, and yes, you would get the interference fringes. Okay, two bright spots. I'm not talking quantum mechanics, I'm just talking waves. Two bright spots, and you say, wait a second, that's not a wave, that's a ray. That's a ray. You have a dark room and you have a room with light. You open the door and the light goes from the light room to the dark room. Do you see any fringes? Do you see any interference? No. You just see a beam of bright light. You might say, well, yeah, but that's a fuzzy beam. You know, it's not a sharp shadow. Well, the reason it's not sharp shadow because the light it's a diffuse light. It comes bouncing around from all the walls in the bright room. But if you look at the laser beam, if you aim a laser beam, it's razor sharp. Okay, laser beam, bright in the beam, dark outside the beam. That's it. So that's like rays. The reason it was so hard to believe that light is a wave and not a ray is because to get the light, the wave aspect of light to pop out, you really had to send it through very small slits that are very closely spaced. So when Young did that in the beginning of 1800s, he said, oh, I see interference, so it's got to be a wave. But you really had to push the experiment to the limit. In conventional situations, when you have doors yay big, you don't get the wave aspect of light to manifest itself. And instead, you deal with rays. Okay? So when the wavelength of a wave becomes much smaller than the geometric size of what that wave goes through, you are in the ray limit. So what matters is the ratio of wavelength to the geometric dimensions of what the wave goes through. If it goes through slits, then what matters is the ratio of wavelength to slit sizes and wavelength to slit separation. When wavelength is much smaller than either the slit width or the slit separation, the wave aspect is hidden. And the energy of the wave or the energy of the disturbance, right? Wave is a disturbance. That energy spreads in a ray-like manner. The reason that you see waves on the ocean, the reason that you see ocean waves, the reason that you think the disturbance of the ocean surface spreads in a wave-like manner is because the wavelength of that disturbance is comparable to things like piers, jetties, your body size, and so on. If you throw a rock in the water, it creates a disturbance. That disturbance spreads out in a wave-like manner that has a certain wavelength. If that wavelength was microscopic, okay, the disturbance still spreads. There's still energy spreading out. You just wouldn't realize that it's a wave-like disturbance. Okay? the energy of such a wave spreads in a ray-like manner. And in that regime, there is no overlap, there's no diffraction, and there is no interference. So if these ratios are much, much less than 1, i.e. wavelength is much, so example, wavelength is much smaller than A or D in a double slit. So this is D and this is A. Okay, the energy of a disturbance spreads in a ray-like manner. So again, with light, only when Young realized that he needs to pass it through very narrow slits that are spaced close together, that's when the wave aspect of it popped. And by the way, he didn't use slits. He used something like a divider, like an index card that sort of separates left and the right. So now, going back to our estimates, because the de Broglie wavelength of a dust particle is much, much less than any dimensions of any experimental apparatus. It was 10 to the minus 15, the minus 13, forget about it. Its wave aspect is not manifested. We will not see any diffraction effects or interference effects with dust particle. Okay, so because lambda of a dust particle is much, 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 much less than any, than dimensions of any experimental it's even less than an atom. We can't build experimental apparati that are that small. Okay, its wave aspect is not manifested. Yes, dust particle is a wave, but it's a wave of such tiny dimensions that its wave aspect is not manifested. So this is your first inkling of how quantumness of everyday objects gets hidden. Okay, we will not see any diffraction effects or interference. On the other hand, the wavelength of electrons is actually comparable to typical interatomic spacing. You can find a metal that matches that wavelength very well. So when we shoot electrons at crystals, we will see diffraction and interference, because de Broglie wavelength of electrons that we calculated, 0.1 nanometer, 1 angstrom, is very comparable to atomic sizes, interatomic spacings, and other atomic characteristic dimensions. Atoms in crystals act like a diffraction grading, periodic position of atoms. And this is why Davison and Germer observed diffraction of electrons off of crystals. But again, if I shoot the same electrons through my door, I will not see diffraction because the wavelength of electrons, that same wavelength, 0.1 nanometer, is much less than the door. So whether electrons behave as waves, i.e. display interference, display diffraction, or whether they do not display those properties, depends not just on the electrons themselves, but what those electrons pass through. There is no such thing as something is small or something is large. Something is small only in comparison to something else. So the de Broglie wavelength of electrons is not small in comparison to interatomic spacing. And so you get strong diffraction effects, you get overlaps, you get interference, blah, blah, blah. But it is small in comparison to the size of my door. So when I shoot the same electrons through my door, I will say, well, I don't see any waves. Electrons act like particles. They carry momentum, but I don't see any diffraction. I don't see any interference. I don't know what you're talking about. Okay? So in summary, in order to obtain an interference pattern, the wavelength, and in the context of particle, the de Broglie wavelength, but in general, wavelength has to be comparable or larger than. If it's much larger, the diffraction is so strong, the spread is so strong that, again, you don't get any fringes. So if you go back to your double slit, if wavelength is 10 meters and the slits are separated by 1 millimeter, what's the separation between fringes? It's infinite. You just get one bright fringe in the center. Okay, so the wavelength cannot be too small, because if it's too small, you're in the ray limit. And if it's too big, you're so swamped by diffraction that ironically, you don't actually see interference. And not all experimental apparati are slits. Okay, we just keep using the double slit, single slit, just to, it's a good conceptual workhorse. And I would add in words that it's not just the comparison of the wavelength to the dimensions of the experimental apparatus, it's also the comparison of the de Broglie wavelength to, for example, resolution of our experimental measurement. Why does it matter that the wavelength of a baseball is 10 to the minus 17 meters? If I cannot resolve my trajectory to less than a millimeter, okay? If the glove was the size 10 to the minus 15 meters, then yes, it would matter that baseball is a wave. So that's, again, along the same lines. You're comparing the de Broglie wavelength on the one hand to experimental dimensions on the other hand. I hope this discussion with a little bit of theatrics drove the point home. Have a good digestion of this material, and I will see you with a complex number hat on.